Okay, so in the last class, we started discussing the read and write operation of SRAM. Didn't get a chance to get to the write operation, of course, but we started with read. So today I will start with a very quick recap of the read operation and then move on to the write and beyond. Okay, because you'll see read and write operation are kind of linked together. They're quite similar in a way that the biasing mechanism uh, can often lead to unwanted write in the read operation. And I'll talk about it in a second. So here is what the 6 transistor SRAM cell looks like. You have 2 back-to-back inverters and 2 access transistors. When you read, you basically pre-charge the bit line and bit line bar to the same level. And what is that level? You pre-charge them to VDD. Okay? And then what happens is, imagine one of these nodes storing 0 and the other one storing VDD. Whichever was storing VDD has no action to take part in because, well, there is no voltage difference between the bit line and the storage node. So nothing happens there. But the node that is storing 0, it starts sharing charge, or basically, depending on how you want to portray that. Either the bit line charges up the node, or you could say that there is a charge sharing, whatever. Different textbooks represent it different way. So this is the actual diagram. And I told you in the last class that every node that you see in the circuit has a capacitor. Okay, so you have a capacitance here. This capacitance shares charge from the bit line and gradually charges up to a non-zero value. Okay, and then in doing so, it discharges the bit line. So you started with both of them being VDD, but after a small amount of time that you use for reading, one of the bit lines will discharge down to VDD slightly less than VDD. Okay, and then you can use a sense amplifier circuit to sense what happened to the bit line. Are you guys all with me so far? Okay, that's how you read. And I told you that depending on where the 0 is, if this guy is 0, the other one is VDD, remember, always the 0 storing node will lead to discharge, not the other node. So if this is the combination that you're looking for, then this bit line will reduce and the other one will remain VDD. Now, if for some reason you are storing the opposite kind of data, VDD and 0, then this one will remain constant and the other one will discharge. So depending on which, as long as you keep monitoring one of the bit lines, it should be good enough. You just want to answer this question. Did this bit line discharge? Yes, sure. In that case, the corresponding node was storing 0. Or, oh, this bit line didn't discharge. So that means the corresponding node was storing 1. Okay, that's how you read. And we also notice the reduced circuit during read operation. So essentially the PMOS here and the NMOS there are inactive based on the biasing scenario we considered. So only these 2 transistors and the other 2 transistors were active. Okay, and between these 2 transistors, there was a situation where this node voltage was going up. And you don't really want it to go up too high because then it will flip the stored data, as we discussed in the last class. So it needs to go up because otherwise you cannot read, but it cannot go up too much. Okay, so who determines the amount of voltage that you get at this node? And we discussed that, the resistance division between these 2 transistors. And we mentioned that this resistance needs to be as low as possible to create some voltage, but not too much voltage. Okay, so that's where this cell ratio came in, where cell ratio is essentially the ratio of the W over L values for transistor 1 and transistor 5, based on this numbering. Does that make sense, folks? We discussed all of this in the last class. So cell ratio showed, we basically looked at this slide as well, like this figure as well, where we noticed that if the cell ratio increases, the amount of voltage that you get at this node gradually reduces, which is good. So you want something non-zero, but you don't want it to be like too big of a voltage. Otherwise, it will disrupt the stored data. Okay, that's cell ratio is one very important performance metric for SRAMs. Now, we are ready to get to the write operation as well. And you'll see how similar they could be in some sense. Okay, so for write operation, I'm considering again that you were storing 0 here. Let me just put it here, basically 0 here and VDD on the other side. It's there already. I don't have to draw, it's there already. 0 and VDD. And you want to write or program something. So when I say program, you basically want to change the 0 to VDD, and you don't have to worry about the other one. Other one will automatically be reversed, right? But still, what we do is we apply the opposite type of voltage to the corresponding bit line. So for example, this node was storing 0. You have to apply VDD to the bit line corresponding to that one. And this node was storing VDD. So I have to, if I try to flip it, I have to apply the opposite kind of voltage to the bit line corresponding to that one. So 0 and VDD. Now they are more like it. Now they are more like bit line and bit line bar. Don't you think? So they are opposite to each other. During read operation, we deliberately made them the same. We pre-charge them. But during write operation, we actually use them in a complementary fashion to switch their stored data. Now, here is how it really works. Can anybody take a look at this diagram on the right that you see and tell me how is it similar, or is there any part that looks similar to the read operation? Is there any part that looks similar? Anything? I told you that SRAM is a symmetric circuit, right? It's as if it has two parts, left and right. Do you see any similarity between what we saw during read operation and here? I can give you a hint. Look at the left portion of the SRAM, the left. What did we do during read operation there? We pre-charged the bit line. So the bit line started with VDD, and the storage node had 0 as well. And then what happened? There was a charge sharing from the bit line. It charged up the node inside, right? Does that make sense, folks? Okay. So looks like when you are writing, you're basically doing something similar, right? I'm going to pay attention and try to make some reasoning. I'm going to ask you a question after 5 to 7 minutes after I go through the process, and then make you think about the similarity and asymmetry between read and write operation. What saves read from accidental write? So let me first explain how write operation works. So when you apply VDD, there is a chance that this node voltage will gradually go up from 0 to some value towards VDD, or more than VDD over 2. And then what? If you somehow exceed VDD over 2, this inverter flips. So it was storing VDD, now it will store 0. The moment it flips, it immediately flips the other side as well to VDD. Does that make sense? So you have to just provide enough voltage, enough encouragement. Remember, you don't have to charge this node all the way to VDD. All you have to do is somehow increase the node voltage slightly beyond VDD over 2. And then one of the inverters will flip. And it will make the other one flip. Done. Okay? All right. One other thing. Essentially, that's not really how the actual write operation occur in SRAM. That's what we hope to achieve, but that's not what happens practically. The flipping starts from a different place, and I'm going to show you that one. You ready for it? It's not like we charge up this node voltage high enough that the transistor flip. It's very difficult to achieve. Instead, we make the other one flip. Remember, there are two inverters. If one of them flips, it will drive the other one quite easily. So you just have to make sure either this one flips or the other one flips. For write operation, we basically target the other one, meaning, remember, we didn't really talk about this other side of the circuit. Okay? I'll ask you two questions in a few minutes. And I just told you that we cannot really flip it. That will be one of the questions, by the way. Why do you think we cannot really flip this one, but we flip the other one? Okay, here is how. So, still with me? I mean, this is a little bit confusing to not have the transistors here, I understand, but this is how the textbook represents it. But I prefer getting back to the basics, like the real transistor, and using that to explain. So please pay attention. So what I was saying is, say this one was storing VDD, and I'm trying to flip it. So I'm going to apply 0 to the corresponding bit line. Okay, so if this guy stores VDD, what is this node voltage? 0. If this is 0, this NMOS is off, right? And this PMOS is off. So look at it that way. So the two active components are this transistor and the other transistor. Okay, is there any kind of charge sharing or charge exchange between any two nodes that you can see here in this region? Can anybody tell me? What is this node voltage? VDD. What is the voltage here now at the bit line? 0. So obviously there is a voltage difference, and there will be charge sharing. In which direction? Basically from the storage node towards the bit line. So it will discharge. The bit line will not charge it up, it will discharge, right? So apparently this node voltage will gradually go down from VDD towards VDD over 2 and lower than that. So we somehow make sure that this discharges farther below VDD over 2, and then it flips, of course. You see that? So instead of targeting this side, we target the other side. I know it got messy after I drew all those stuff, but did I make any sense at all to you guys? Okay, don't worry, we'll revise it. Like, we'll go over this one more time. But before we do so, let me ask you this question. Why do you think we don't really try to flip this one, but try flipping the other one during write operation? Thank you. Why is M1 stronger than M5? We made it stronger. Remember that? So when you design the read, operation, you made sure you don't have accidental read operation. In doing so, you somehow made M1 basically weaker or stronger. Which one? Which one did you make weaker? Remember, during read operation, whom did you make weaker? M5 excess, because if it is too strong, it will basically disrupt the stored data, right? So we made this one stronger, meaning its resistance was lower. There are 3 different ways of expressing that: making M1 stronger, or making it lower resistance, or making its width bigger, however you want to portray that. So we designed it already, and we made sure that it's difficult for you to create high voltage at this node. That was by design. That's why I started to talk about the read operation today again, to remind you. Okay, so we already designed it. Now during write operation, you are left with the same structure. You are not going to change the transistor, right? During read and write, they're the same transistors. So now you are basically struggling to achieve write because you have just designed it quite opposite to that. So you rely on the other 2 pair. Remember, I never commented about the PMOS strength, did I? I did not. So we make sure the PMOS is as such that, the relative strength between this PMOS and M6 will be as such that M4 will be weaker and M6 will be strong enough to basically flip it. Does that make sense, folks? Okay, a circuit is complicated. There are so many different components connected to so many different nodes. There are other ways to look at it. See, this transistor is active and the other transistor is active, and this guy is connected to VDD, and this node voltage was also VDD. This is 0. You see that now? It's much easier to see. Okay, what I'm telling you is now there is a motivation for this VDD to gradually discharge, and you have flipping from VDD down to VDD over 2 and below. There you go. But there is a catch. There is a problem. Can anybody see the problem there? Is it that easy for me to say, oh, this node voltage will discharge? There is a factor which will basically act against this discharge. What is that factor? Where is this PMOS connected to? VDD. Basically, when the PMOS is active, it is connected to VDD. So as you lose charge from this node, don't you think this VDD will replenish the charge? Right? In one way, like through this route, you are trying to discharge, but through the other route, you're trying to charge it up, charge it back up. Does that make sense? How can you still ensure, because even though there is a fight, one of them wins? Who is helping with the discharge? The NMOS, M6, right? And who is helping with the opposite, PMOS? Who do you want to win during write operation? Of course, the access transistor, M6. So obviously, the logic is you make M6 stronger, quite opposite to the read operation. Remember, we made the access transistor weaker deliberately. But now, considering the write, you need to make the access transistor stronger compared to the PMOS. So that during write operation, despite its best attempt to replenish the stored charge here, it will not be able to do it soon enough, and the NMOS will win eventually. Okay, so notice how interlinked, and you haven't even seen the complicated part here, right? I'm just hinting at how complicated things can be. Like there are few components, but they all ask for different stuff. Okay, now you need to make this PMOS weaker and the NMOS stronger to ensure successful write operation. Are you guys all with me so far? So did I tell you, when you read, you always read from the same side? Didn't I tell you that? Because there is no point trying to read from the other side, because whatever you read here, the other side is storing exactly the opposite. Why would you try to read that? So we never try to read the other side. We make sure that we optimize a side for read operation. So this guy is stronger, this guy is weaker, and whatnot. But then the other side is typically optimized to facilitate write. Because if this guy flips, it will tell its friend, hey, I just flipped. You should also flip. So that's why the cross-couple inverters come in. Okay. So now that you have some idea about how the write operation works, let's discuss what you need to achieve there. And I just explained, basically, without going into this expression, that between these two transistors, there has to be a relative strength mismatch. Okay. So we represent that strength ratio as another factor called pull-up ratio. Okay, the ratio between the width W over L for this transistor and W over L for number 6. Are you guys all with me? Okay, this is called pull-up ratio. Why the name pull-up ratio? Because these transistors, the PMOS is pulling this node up. So PMOS transistors are called pull-up transistors, and NMOSs are called pull-down transistors. So you're basically acting against the pull-up feature of the PMOS already. That's why they decided to give it the name pull-up ratio. Now, tell me one thing. You want M6 to be stronger, right? Don't you think? You want M6 to be stronger. That means, how can you make a transistor stronger? By making it bigger. So it's W over L for M6 should be higher than that of number 4. Don't you think? If that is the case, this is the denominator. So your pull-up ratio should go down. The lower the PR is, the lower the pull-up ratio is, the better it should be for write operation. Is that logical? Okay. All right. So notice, lower pull-up ratio. So this is a real data taken from a source, as you see. This shows voltage fall of node storing 1. What does that mean? So this node was storing 1. You were trying to reduce it down to whatever lower voltage than you can get to. At least less than VDD over 2, if possible even more than that. Remember, you are trying to write. So do you want the voltage fall to be more or less? Tell me. Do you want the voltage fall to be more or less? Basically, I'm using the same terminology as the data here. Not less, by the way. The more the voltage falls. So basically, what are you trying to achieve here? You're trying to flip it. It's write operation. You're trying to change 1 to 0. Or 1 is VDD here, by the way. So you're trying to reduce that voltage to whatever amount is possible for you, right? So the lower you can get, the better it is. So which direction is good? This direction, don't you think? And notice pull-up ratio is getting lower, as we thought about based on this argument. I know, like, there are too many things. This should go up, this should go down, this should be stronger, this should be. There are too many things to keep in mind. Obviously, there is no way you can memorize this. Okay, think about it logically, and trust me, if you think about it by yourself without listening to me again, just sit with pen and paper and look at the circuit and see what you're trying to achieve and double check with the trend. And my recording is already there. The comments are also added to the slides. So just double check whether it makes sense with what I'm saying. If it somehow contradicts, then you should come and talk to me again. If not, then there you go. And trust me, once you know how to basically look at the circuit and decide on different design factors, you're basically learning the real engineering. That's what the engineers do. Nobody knew when they thought about SRAM that you have to fight with this and that, right? They learned it by doing it. So apparently that's how engineering works. It's an optimization problem. This is the final slide of this lecture, as you see, okay? And this will indicate how complicated the design space of an SRAM is. And I'm going to show you that, okay, in a second. Let's see. Imagine you want this SRAM to be really stable when it's storing data, meaning you need better read stability. So when you read, you have to make sure that it doesn't accidentally flip the data. But folks, remember, in this side, when I'm writing it, forget about the other side, which was successful. But during read operation, don't I try to do almost something similar like VDD and 0 and try to charge up this node? Isn't that similar to the write operation? Quite similar to the write operation. But that means there is a risk. Yes, there is still a risk that accidentally you might flip it. If you read for too long, if you give it too much time to charge up, then it will flip. Don't you think that? So we read very quickly. We don't give it enough time to increase the voltage beyond a certain level. There is one other factor that saves us from accidentally reading. And I was going to ask you this question. That's why I didn't mention that willingly. What was the difference in the bitline biasing during read operation and write operation? I used a term specifically during read. Thank you. I told you there is a difference between pre-charge and drive. There is a reason why I highlighted that in the last class. Pre-charging means you just charge it up and just let it go, right? It will keep discharging. So imagine something is plugged up to the wall. It will never lose charge. It's always being replenished. But something, you charged it and you just took it out. So it will continuously lose charge. So similarly, during pre-charge, you don't drive it. So the bit line is not as strong. It will not be able to just keep charging this node and eventually disrupting it that easily. But during write, you make it strong by driving it. I didn't say during write, you pre-charge the bit line. I said you drive the bit line. So that's the other difference between read and write. During write, you drive. During read, you pre-charge and let it go. So it's easy enough to say, it's difficult enough to do. For that, you need specialized circuitry, which you charge and let it go. And then during write, it has to make sure it has a constant voltage applied all the time. So we have peripheral circuits that, yes. I'm sorry, could you repeat that? Mm-hmm. Mm-hmm. Absolutely. That's a great suggestion, honestly. I'm so happy that you mentioned that, honestly. The reason is this shows that you guys are paying attention, and please do that. Please feel free to suggest. Couldn't we have done that? Couldn't we have done that? Honestly, this is a technique that we often use. Actually, we use the opposite technique, but it's kind of similar. So what he suggested is to avoid accidental flipping, instead of using full VDD during read, couldn't we have used a smaller VDD to make it a little bit more, safer? Maybe VDD over 2, slightly higher than VDD over 2, but not really VDD. That will make it safer, right? Don't you think? People tried the other thing, actually. They optimized the SRAM for read operation. They chose a VDD that was small enough that it doesn't lead to disruption. During write, they basically use more VDD. So VDD plus something, so make it stronger. So it's called word line overdrive. Okay, so you basically overdrive. But what you suggested is exactly the right approach. You could also underdrive. So during write, you do something. During read, you underdrive. That's also fine. So overdrive versus underdrive doesn't matter. This is actually a technique that is used. So there you go. You invented something. If it were not taken already by the engineers, you could have had something there, right? That's how things come into being. Like somebody thinks of an idea. Can we do that? Sure. Given that other people haven't already done it. There is a challenge, by the way. My PhD advisor used to tell me all the time, there is no free lunch in engineering. And I see that every day as I work towards different stuff. So it's easy enough to say again, but turns out if you need two different voltage sources, if you see the layout, how many of you have worked on layouts? 433, anyone? Okay, 335, I know we don't cover layouts, but at least 433, if you have taken 433, at least to some degree. And don't worry, I'll show you some layouts in this course. It's not a layout related course, but I will show you something. Okay. So when you do layout, you have a VDD bus and you have a ground bus and you connect everything else between them. So remember, if you need two levels for overdrive and underdrive, you need two VDDs. That means there will be an additional line. And that is a nightmare for area scaling. I told you, we want to make things as small as possible. You are going against that. So if you are so desperate that I have no choice, then you can do it. But for the most part, it's not useful for regular applications, unless it is like highly specialized. Okay. All right. Now, let's move on to the slide again. So for read stability, let's try to make sense of these comments. Otherwise, these will be just random bullets. Okay. But let's try to make sense of it. Reduce the excess transistor width and increase the pull down transistor width. Let's see. This is the pull down transistor because it pulls down the node to ground. And this is the excess transistor. I just told you during read operation, you don't want this excess transistor to be so strong that it will accidentally change this node, right? So you make sure that the excess transistor is weaker than the NMOS. So see, this part, just the read stability part, is asking you to reduce the width. Reduce the width. Notice, why are we connecting it to the width? Because that's the only thing that the engineers can change during design phase. Notice that? You cannot just dynamically make it strong or weak. Well, technically you can, but practically it's difficult. So we don't do it. Okay? So reduce the width and increase the width of this one. Okay. So let's see what happens to the better write stability case. To achieve better writability, and trust me, the next slide that I'll show you will make it so apparent, so visible. I really like that paper where those things were presented. I'll show you in a few minutes. But let's go through this. So better write stability, I just told you that you need to increase the excess transistor width, here, and reduce the pull-up transistor width. So this should be reduced based on the discussion that we just had, right? Now you want to make sure this is strong enough to fight against the PMOS. All good? Okay. So far it looks manageable. Like we just make the NMOS strongest, and then this NMOS strong, and the PMOS weakest. Right? Sounds doable. The PMOS should be weakest, meaning the smallest in size. Excess transistor should be somewhere in the middle, and NMOS should be bigger, like super big, right? As big as we can get. So between these two, it sounds doable. It's not a big deal. Let's go to I'll get back to this later on, but let's talk about this one first. Better hold stability. Better hold stability. What do I mean by that? Remember, when you're not reading, we are just talking about reading and writing, but you will not be reading and writing all the time. There will be idle time as well. So the SRAM will be just holding on to the data, not doing anything. And notice SRAM relies on a really delicate balance between two inverters. They drive each other. They don't disrupt. If one of them randomly flips, the other one will immediately flip. And there goes your data, right? So when the SRAM is holding the information, you're not reading or writing, you have to make sure that the data is really stable. Why is that? Because remember, our world is not perfect. There is always noise. There is always thermal noise, voltage noise generated all the time. There are multiple sources of noise in the circuits. And because of noise, if zero becomes, for a second, if there is a spike that comes in and the zero slightly becomes close to VDD over 2, there you go. You have a flipping right away. Okay. So what saves the SRAM is the delicate balance, the noise, and we'll talk more about this noise stability. And hopefully it will be clear like two, 3 slides down the line, what I mean by that. So trust me for now, that to achieve the better hold stability to make sure when you are not reading and writing, the SRAM will be able to hold on to the data well. You need perfect balance between NMOS and PMOS. I gave you a hint about this voltage transfer characteristics. Remember, V out over V in a CMOS inverter. Did I tell you that in one of the previous classes? That it's VDD over 2 where the transition occurs. And I also gave you an example. Imagine if you have a VTC that looks like this. What does that represent? That represents the NMOS is more powerful because it's taking it closer to ground easily. And right, NMOS more powerful. What does that mean? NMOS more powerful means it has more, it is wider, its width is higher. Aren't you doing exactly that by asking one of them to be weaker, the other one to be stronger? So you're basically changing the VTC position, which is not good. You want it to be identical in both directions. So for perfect balance, you want balanced sizes of pull down and pull up transistor. Does this point make sense to you guys now? It's not just a point. It's definitely a requirement. But that goes against what? Goes against the other two. Read stability, write stability, and hold stability. So now you are starting to look at design conflicts. There are design conflicts everywhere in most memories that you will learn about. You try to improve one, the other one suffers. So you have to find a way to optimize. You cannot sacrifice one or the other. Okay. All right. Let's talk about the excess time now, which is more secondary. If you want to make things faster, like I will read fast, write fast, then who leads to read and write? These excess transistors. If the excess transistors can provide more current, there will be better speed in read and write. So to achieve that, you want these excess transistors to be bigger in size so that they could provide more current. But then they're acting against the read stability. So there you go. I mean, for lower access time, you need to increase the excess transistor width, but that's not really helping with the read, right? One other thing, lower cell leakage. What do we mean by that? So remember, you have a memory array. Maybe you have millions of SRAMs. You are going to read just one of them. What will happen to the others? They're not being read. They're not being written. They will be in hold mode. They will basically just hold on to the data. Okay? Did I tell you about leakage current or off current or subthreshold current, right? I told you the transistors are always leaking, right? Okay, so one thing about the leakage is if the transistors are bigger, they leak more, of course, as you can imagine. So if you have bigger transistors, they will leak. Millions of them leaking will lead to nightmare. So the way to reduce the leakage, one of the ways is to minimize the size of the transistor. And there is one other reason to minimize the size, area. I mean, simply because you need to make the NMOS strong doesn't mean you can just make them big, right? Because you have to save area. So minimum size is kind of a requirement for most designs. That goes against both read stability and write stability, right? It's basically sacrificing everything. And obviously cell area that I just explained. So some requirements require your transistors to be perfectly sized, balanced with each other. Some require them to be as small as possible. Some require them to be big. So how do you survive with all this fighting, right? That's the challenge that engineers deal with every day when they work on SRAM design, per se, for any memory design. And the first slide in this lecture that we'll start today will hopefully make it more apparent. So this is taken from a research article that is published. It's one of the top conferences in a circuit design field, ICCC. So, well, this really nicely presents the read optimized design and write optimized design. Notice, I know there are many other components which you haven't talked about. It's okay, it's besides the point. I just wanted to take this figure from the research article directly without any modification and show you how it looks. This is the SRAM cell that we have all been talking about, right? They've just drawn it in a different way, but it's the same thing. And what are this? These are the circuitry. These are the peripheral circuitry that we are yet to discuss. So it's okay. We'll discuss them later on. What I want you to focus on is look at this legend. So for read optimization, wherever you see the red marking or red transistor, you are making them larger, or you need to make them larger. and the blue ones you need to make smaller. That's what the read optimization require. Okay, so now take a look at this, only this SRAM cell, and compare it against the other SRAM cell, which is write optimized. Do you see any difference here? Basically, exactly opposite to each other. Whatever you need to do to optimize your read, make it better or more stable, you need exactly opposite to make your write operation better. Like I don't think there would be any better representation of that, right? There are other things, by the way, which we are yet to discuss. Like I said, there are other components. Notice here, there are some blue transistors here, some red transistors here that are related to sense amplifiers and drivers. We are yet to discuss them, so I'm not getting into that one. But not just within the cell, but also within the peripheral circuitry, there are conflicting requirements. If your peripheral circuit is so and so, it will not help with the write. It will help with the read and so on. And there are conflicting requirements everywhere. But remember, your transistors will not change from read to write. They will be the same. So what do? If you make them smaller, they will remain small. Make them larger, they will remain large. So you have to find a way to optimize. Okay. And notice you cannot make everybody happy. So what do? Typically in SRAM design, we make all of them minimum sized. At least we're getting something. Make all of them minimum sized and then try to do something to make read and write work. Okay, that's the strategy that most engineers decided to take eventually. And man, we are so tired of this fight. Like, okay, we lose one way or the other. So let's just go with the minimum size. At least save area, save leakage, because that's killing us. And now find out interesting engineering techniques to make read and write work. Like, for example, one that you suggested, overdrive could be one option, or other interesting techniques. Okay, so move on to the next one. This is where I was going to talk about hold stability. That's why I didn't spend that much time here. How many of you remember this voltage transfer characteristics? Just like a few minutes ago, we discussed this, right? Output versus input characteristics of an inverter. So instead of output input, I'm just writing V1 and V2 because we are now going to focus on the SRAM cell itself. So imagine this is your V1 and this is your V2. This will be the voltage transfer characteristics for one of the inverters. And for the other one, input is V2 and output is V1. So basically the opposite, exact opposite to what you are looking at here. And now to look at them together for the entire system, cross-coupled inverter, you just put them on top of each other. Does that make sense? Did we see that before? Remember in the previous lecture, right? Regenerative action of inverter. So essentially the butterfly curve again. So why back to the butterfly curve? Let me explain. So there is a concept called static noise margin for hold operation. So we'll start with that. When your SRAM is just holding on to the data, you're not reading it, you're not writing anything. You have to make sure that the data is stable enough that it doesn't randomly flip automatically because of environmental aberration, because there is a lot of it. There is a lot of aberration, okay, from coming from here to there. So how do you ensure that? And the way people represent the aberration is by showing that you have noise sources, as if you have voltage sources built into the SRAM cell. So this VN represents noise voltage source, okay? So there are noise voltage source that is trying to flip this inverter. There is another noise voltage source that is trying to flip the other inverter. If one of them flips, there you go, okay? So how does this, butterfly curve look like with this noise voltage source? Are you guys still with me? So we see what happens to the voltage transfer characteristics when you impose additional noise from environment. And if you simulate them, it basically goes from the dash line to the solid line. So depending on what type of noise you're imposing, one of the lobes become smaller. And I can explain, basically, you don't have to memorize. Notice, let's use same color to draw one type of line. So maybe this one, green one was balanced, perfectly balanced. And with noise, maybe it shifts a little bit. Okay. Red one was perfectly balanced, but with noise, it shifts a little bit. Do you see any change here, folks? I just shifted, right? Didn't I? I just shifted with noise. Noise voltage source shifted it a little bit. Now, what do you see? The solid lines created really nice, perfect lobes, butterfly wings, balanced butterfly wings. But the dashed lines are creating imbalanced butterfly wings, don't you see? And that's exactly what you see here, solid and dashed line. One of the lobes got bigger, the other one smaller. Does that make sense? Remember, these lobes are related to the noise margin. The bigger the lobes are, the more stable the overall data is. I'll explain in a second, but let me first try to make the point, make the comment, and then I'll explain why that is the case. So the bigger the lobes are, the more stable your data is. And basically, the biggest lobe that you can make is when they go through VDD over 2, right? As you can imagine, that's the biggest you get, not more than that. Okay, so if the lobes become smaller, that's bad news. Okay, notice one more diagram. Okay. So this is a slightly shifted version of an SNM for hold operation. And what is the red one? Just try to visualize this. I mean, I cannot show you an animation here. Imagine if this lobe keeps getting smaller and smaller, right? The other one remains the same, but this one gets smaller and smaller. Meaning this solid line shifts left, this dashed line shifts right. And if they keep doing so, at some point they'll overlap and you end up with this type of a situation when there is no lobe. That means one of the inverters will flip randomly because of the noise. Are you guys all with me so far? So when noise comes in, it shifts the VTC. When one VTC shifts, the other one also shifts. They shift it in a way as long as there is a lobe. As long as there is a lobe, like it could be a really nice, like a tiny lobe. But as long as there is one, the data will be safe. But the moment it crosses over, the data is gone. Make sense? So you can only take as much noise as the lobe size, basically. That's why the bigger the lobes are, the safer the data is. Okay, so let me take a step back and tell you that one more time. So the most ideal VTC is the one that is balanced. Let me ask you this question. Why do you think the balanced is better? What if I have a really big globe and the other one is really tiny? Wouldn't the big globe be better? Why not? Yes, remember, if one of them flips, like two lobes represent two ends of the inverter. If one of them is ores, that one will flip, right? If one of them flips, the other one will surely flip. So yeah, I'm stable, but my friend is not. When my friend flips, he or she will make me flip for sure. So no point. So you have to make sure that you give them equal balance. That's why the best case scenario is when you have perfectly balanced lobes, as big as you can get, but they have to be balanced. When you impose noise, depending on what type of noise, is it positive here, negative there? What is the polarity of the voltage? Depending on that, one of the lobes will suffer. Other one will benefit, by the way. Whatever affects one will help the other, but doesn't matter. You need both of them to be stable. That's the problem, okay? So one of them, maybe this lobe will shrink, the other one will get bigger, or quite the opposite. Doesn't matter. As long as there is a lobe, you are still safe. But if the noise is so much that it basically leads to this type of non-overlap, then you flip. Does that make sense, folks? So there are research articles that basically mathematically measure, and I think in one of the classes that I offered, I shared the paper as well, that deduced mathematically geometric relationship between the lobe size and the static noise margin. By the way, I forgot to mention what that is. Static noise margin is the measure that we use to represent how stable the STM is to noise. Okay, why static? Because it's just holding on to the data. There is no dynamic change. Nothing is changing with respect to time. It's just holding on to the data, right? Okay, so where did I write it? Yeah, right here. Right here. Notice this. This is a very important point. Okay? Static noise margin. How do you measure static noise margin? Basically, if you're given this blue lobes, you fit 2 squares. You fit 2 squares inside the lobes. Notice that. The bigger the square. Oh, can you not write draw a smaller square? Yes. Forgot to mention the biggest square that you can fit within the lobe. Take that square. Take the biggest square that you can fit within the lobe. And the side of the biggest square, well, it will be measured in volt, as you can see, because the x-axis is volt, y-axis is also volt, right? The side of the biggest square represents the SNM number for the SRAM. It's not random, like we didn't make it up. There is a big research paper that deduced that, hey, you could measure SNM this way. Previously, by the way, the other way to do so would be experimentally measure it. Take an SRAM cell, impose noise, 100 microvolt, 500 microvolt, 1 millivolt, 10 millivolt, and see where it flips. Oh, it can take up to like 50 millivolt. There you go. Your SNM is 50 millivolt. That's your margin, noise margin. That's the margin you can take. Make sense? But rather than always trying to measure with actual experimental noise injection, we could always do it from math. That was proven in a research article. Okay, does that make sense to you guys? All right, so what if you have a situation like this where the lobes are not identical? Here is what you do. You fit largest square in both of them. You take the smaller one and you take the side of the smaller one. That's your SNM. Why? Why? Because you always report the worst case scenario. Remember, if one of them flips, you're done. Like if you always provide the rosy picture that, hey, we have enough security, that's not it, because the other one might flip sooner. Okay, so always take the worst case scenario. Whichever is smaller among the lobes, fit a largest square within that lobe, and the side of the largest square will give you the SNM. All right. Okay, so one more thing to point out. So we covered this. We covered this as well. How do you measure SNM? How about this one? I'm going to show you some realistic picture. In a memory array, you have millions of cells, millions of SRAMs. Remember, when we make semiconductor chips, if you make 10 of them, they will all be different from each other. It's practically impossible to make them perfectly identical to each other. Okay, this is known. Am I making sense? So if you have 1 million SRAMs, there will be 1 million types of SRAM with minor differences in characteristics. Because of that, you always have a distribution. I cannot mention that my SRAM has an SNM of 50 millivolt. I can show you a distribution of SNM because some SRAMs will be better, some will be worse, some will be mediocre. So in between, you have a distribution. This is how it really looks like. Am I making sense? So when I told you, take the worst case scenario between these two lobes, that's for one SRAM cell. So you take the worst case between the two lobes in one SRAM. But there are millions of such SRAMs. You take worst case for all of those million SRAMs. Making sense? You have millions of SRAMs. You take the worst case scenario for SNM for all of the million SRAMs. This is what you get, a distribution. And you take the worst of this distribution. Right? You are basically choosing the worst every time. Within one SRAM, take the worst lobe. Between million SRAMs, report the worst lobes all the time. And then you have a distribution. And within that distribution, what is the minimum SNM? That's your SNM for the technology that you're dealing with. Right? You have to make sure that not even a single one fails. Not even a single one. Because remember the slide with cat and bat that I had? One bit of information can change cat to bat or bat to cat, right? Similarly, one bit of information could lead to disaster. You cannot let even one of them flip. So when you measure this, you have to make sure that you keep your system in a way that it doesn't lead to more than 0.27 millivolt. Look at that SNM number, 0.27 millivolt noise. So you have to make sure smaller than that. Okay? Or you do something to the design to do this, shift it to the right. Why is that good? Why is that good? Because notice your minima has shifted. Okay, I'm going to show you one more thing. As an engineer, like here's how you should think about stuff. Is this any good? Is the black one any good? Why not? It doesn't matter. Oh, I've improved the mean. And you'll see that in some research paper as well. People show that, oh, I've improved it. But you didn't, because you didn't really change the worst case scenario. Okay, that's all that matters. Okay, so just keep that in mind. All right, so moving to the next one. Read S&M. So there is a static noise margin for hold and static noise margin for read. Good thing is our time is up, so we can start from read S&M in the next class, which is fine. Right? So think about all the stuff that we talked about. It's a lot to digest, I know, but trust me, if you think about it yourself, don't rely on me, then things will make a lot of sense eventually. Thank you.